We'll start our understanding with temperature with the law of conservation of energy, which states that energy cannot be created or destroyed, it can only be transformed from one form into another. So using that classic example of an object falling towards the ground, we know that when it starts, it has some height. Therefore, it has some potential energy. Let's just say it has 100 joules. As it falls, it's gaining speed. And height is going down. So the potential energy is converting into kinetic energy. So if it had 100 joules of potential at the top, how much kinetic does it have at the bottom? 100 joules. That's right. And you can honestly know anywhere in between roughly what the kinetic and potential is. So say the halfway point, how much potential do we have? 50 joules. How much kinetic do we have? 50 joules. They add up to being 100 total. And that's the other thing about the law of conservation of energy. The total amount of energy in a system always stays the same. But what about when we were looking at the car and you were seeing how the speed matched up with the height? Remember that we first started by measuring the height that the car was at some location and then calculating what the potential energy was. Using the law of conservation of energy, we said that this energy we calculated at the top must also be the kinetic energy the car had at the bottom. But every time we did that, our predicted speed, I'll say V predict, was always greater than the V actual, the one that we measured. Sorry if that's a little rough, I am using a little stylus on my iPad. But it was always greater. Does that violate the law of conservation of energy? Shouldn't energy always stay the total and the same amount throughout the system? The answer is no. So where did it go? What did we say it always goes to? What did we say always affects the motion of an object? Think about it for a second. I'm writing it. Friction. Friction is the reason why objects are going to ultimately slow, because it's sucking energy out of the system. And it's sucking energy out of the system in the form of heat, in the form of thermal energy. So what really is thermal energy? What is heat? What is hot and cold? Down on the molecular level. So if I were to look really close at what's happening on my hand and got down and saw all the molecules and atoms interacting, what I would see isn't what we see normally. You would see violent motion going on, like crazy. Violent motion. And what's happening is all of these atoms and all of these molecules are vibrating and jiggling and jiggling. It's actually a form of kinetic energy, because kinetic energy is all about mass in motion, and these atoms and molecules are in mass and they're moving around. And that's what temperature is, and that's what thermal energy is going to be. It is these atoms and molecules vibrating back and forth. The more you vibrate, the more temperature you have, or the more thermal energy you have. The less you vibrate, the less temperature, the less thermal energy. I recommend watching this YouTube video. You can either type in the URL that you see right up here, or go into YouTube and just search jiggling atoms. The man's name is Richard Feynman. He's a well-known physicist, and he does a beautiful job of explaining what's happening with hot and cold. So check it out on your own time. Here are our learning goals for the remainder of the video. Define temperature in terms of the motion of atoms and molecules, which we've already discussed some, and describe the relationship between thermal energy and temperature. And I'm actually going to tack onto this and say thermal energy, temperature, and something known as heat. So that'll actually add to our understanding. Don't worry about the middle one for now. I've blanked it out. We're going to come back to that in another video. This is what temperature really is. We know that atoms and molecules are in constant motion. Even in a solid object, they're constantly jiggling and shaking and moving. And this back and forth jiggling of atoms is caused by thermal energy, which is a type of kinetic energy, because you have to imagine that all of this motion is velocity. And if you have velocity, and if you have mass, then therefore you have kinetic energy, because kinetic energy is all about mass and velocity. So, what's the difference between temperature, thermal energy, and heat? Let's take a look down below. I've defined them down here. So, thermal energy is the total amount of kinetic energy of all the particles in an object, while temperature is the average kinetic energy of all the particles in an object. What's the difference? What's the difference between total and average? Think on that for a second. So take a look at this. This is a representation of a bunch of different molecules or atoms bouncing around in some space. Notice that they're all not moving at the same velocity. Therefore, they all don't have the same kinetic energy. Remember, kinetic energy is based off of velocity and mass. So thermal energy would be the total of every little bit of these molecules. Add up all the kinetic energy, and that is the thermal energy. Where temperature is going to be on average, how fast are all of these molecules jiggling? So they're both related. One is all the energy, all the kinetic energy in an object. One is on average, how fast are they all jiggling? And heat, what heating is also a relationship between those two. When you heat something, you're taking the thermal energy of one object and you're transferring it to another object. And it only happens when there's different temperatures between the two. So say if you had two things that were sitting next to each other touching and they both had the same temperature, no heating is going to go on. Say, just for a representation, the blue means they have the same temperature. But say that one of them was much hotter. So now this one's red is going to represent hot. So this one's hot and the right one is cold. Well, what happens is because there is a temperature difference between the two, there's going to want to be some transfer of energy. And the energy is going to want to transfer from one to the other. Which one do you think is going to want to transition over? Do you think the one that has all that fast motion jiggling is going to go into the slow and give their energy to the slow ones? Or can something that's moving slow make something that's moving fast go slower? That's kind of confusing. The answer is always going hot to cold. That's the direction of heat movement, from hot to cold. With that, we're going to pause and we're going to talk about this more in class.